Welcome to the deep dive.
Yeah.
Imagine for a second that you just purchased a $500,000 piece of precision engineering.
Right, a serious piece of equipment.
Exactly. You set it up perfectly on your shop floor. It is cutting aerospace-grade steel like it's absolute butter.
Which is exactly what you paid for.
Yeah, but then, say, 6 months later, it starts vibrating so violently, it essentially shakes itself to death.
Wow.
And the craziest part is the culprit isn't a broken motor, it's not a dull tool or, a bad operator. The culprit is literally the dude under your floorboards.
It really sounds like a ghost story for engineers, but it is a daily reality in advanced manufacturing. You're dealing with these dynamic, completely interconnected systems.
Right.
And in those systems, the symptom is almost never sitting right next to the disease.
Okay, let's unpack this. Today, we are taking our stack of sources and doing a deep dive into the silent, invisible destroyer of precision manufacturing, which is machining vibration.
Specifically in slant-bed CNC lathes.
Yes, exactly. Our mission today is decoding how these vibrations cascade through a system, how to diagnose their true origins, and then how to systematically destroy them.
It's a huge topic.
It really is.
Yeah.
And look, even if you are not a machinist, even if you've never stepped foot in a factory in your life, stick with us.
Yeah, there's a lot to learn here.
Because this is a fascinating masterclass in diagnosing complex systems. I mean, if you've ever tried to figure out why a massive project at work is failing,
Or why your car makes that weird rattling sound at exactly 62 miles an hour.
Yes, exactly that. The diagnostic logic we are applying today is entirely universal.
To give you a mental picture of the hardware we're dealing with, slant-bed CNC lathes are built to be absolute powerhouses.
Right.
They have these inherent structural advantages just by design. The bed, which is the main frame of the machine, is angled.
And that's on purpose, right?
Exactly. That geometry is fantastic for chip removal because gravity just pulls the waste metal right down and out of the cutting zone.
Makes sense.
And that same gravity actually assists with contact stability, so it keeps the carriage incredibly well supported.
So they're essentially these giant blocks of iron designed to be totally immovable.
Mm-hmm.
But our texts make it very clear they are not immune to the laws of physics.
Not at all.
Vibration in these machines isn't just some surface-level nuisance. It is a full system disease.
Yeah, that's a good way to put it.
Because the moment you push past that stable cutting zone, the immediate penalty is ruined surface quality on whatever you're making. You get chatter marks, roundness errors.
Rejected parts, basically.
Right, rejected parts. But the hidden damage is so much worse. The vibration creates these repeated impact loads that chip the expensive cutting tools.
And it doesn't stop there. Those shocks travel backward, steadily destroying the machine's own internal components.
Which is terrifying.
Yeah.
And the instinct on the shop floor is usually, it's a panic response. Operators hear the screaming noise of the vibration, and they just aggressively dial down the cutting speed.
Just to get the shaking to stop.
Exactly. But doing that completely disrupts the production rhythm. You are sacrificing your efficiency just to put a Band-Aid on a systemic failure.
Right, and before we can fix the failure, we really have to isolate the enemy. On the floor, everybody uses this catch-all term. They just call it chatter.
Chatter, yeah.
But our sources emphasize that treating all vibration as just chatter is a critical diagnostic error.
Because there are actually 3 distinct faces of vibration.
Yeah.
Right. And you cannot fix the machine until you know which one is actually attacking it.
Exactly. The simplest of the 3 is free vibration. This comes from a singular, isolated impact.
Okay, like what?
Picture a small shock when a heavy block of steel is first clamped into the chuck or, the exact millisecond the cutting tool makes its initial contact with the metal.
Just that first hit.
Right. The machine structure absorbs that single hit of energy, the vibration ripples through the iron, and then it quickly fades out.
It's the tuning fork effect. You strike a tuning fork once, it rings loudly for a second, and as long as you leave it alone, the acoustic energy just naturally dissipates.
Yeah, into the air. It's relatively harmless unless you are constantly hitting it. You'd only really worry about free vibration if your initial clamping process is incredibly violent.
Got it. Okay, so what's the second type?
The second type is far more insidious. It's called forced vibration, and this is driven by repeated external forces that just do not fade away.
Okay, keeping with the analogy, if free vibration is hitting the tuning fork once, forced vibration is like someone sitting next to you, repeatedly tapping the leg of your chair to the exact beat of a song.
Just tap, tap, tap. endlessly.
Yeah, that would drive anyone crazy.
And inside a lathe, that rhythmic tapping could be a slightly unbalanced spindle rotating, say, 3,000 times a minute.
Oh, wow.
It could be a chipped gear in the transmission, a vibrating hydraulic pump, or even an environmental factor, like maybe there's a heavy forklift constantly driving past the machine.
So the force just repeats at a fixed, inescapable frequency.
Exactly. And the real danger here is resonance. Every physical object has a natural frequency, a specific pitch where it sort of wants to vibrate.
Right, right.
If the frequency of that external tapping happens to match the natural frequency of the machine bed, the vibration waves overlap and they amplify massively.
Like an opera singer hitting the exact pitch to shatter a wine glass.
Perfect example. The glass naturally vibrates at that note, the singer feeds it more energy at the exact same note, and the structure just tears itself apart.
Man. But as destructive as forced vibration is, the sources single out the third type as the ultimate nightmare for machinists.
Yeah, self-excited vibration. What's fascinating here is that the cutting process essentially creates its own excitation. It feeds itself.
Without any external unbalanced gears or heavy forklifts.
Exactly. The tool makes a pass across the spinning metal, and due to just a tiny fluctuation in cutting force, it leaves a microscopic wavy ripple on the surface. When the part spins around for the next pass, the tool hits that wavy ripple. That uneven surface forces the tool to bounce slightly.
Which carves an even deeper wave.
Yes, a much more severe wave into the metal.
I was reading this section, and I instantly thought of driving down a washboard dirt road.
Oh, yeah.
You know how those violent ridges form in the dirt? One single truck hits a slightly soft spot in the mud, the suspension compresses, and the tires dig a tiny groove.
Right.
Then the next truck comes along, its tires drop into that groove, the truck bounces harder, and it carves the groove twice as deep. Before long, the road is a sequence of violent ridges that will basically shake your car apart.
That is the exact mechanical loop. The vibration causes a wavy surface, the wavy surface causes more vibration, it spirals out of control in fractions of a second.
And escalates into that terrifying high-pitched scream.
That is true self-excited chatter. Because the system itself has fundamentally lost stability, you cannot just go looking for a loose bolt.
Which brings us to a really fascinating pivot in the research. If a machine is suffering from severe chatter, the logical assumption is that the machine itself is broken.
Like the spindle is shot or the tool is weak.
Exactly. But the texts reveal that the root cause often has absolutely nothing to do with the machine. It starts with the actual ground beneath our feet.
The foundation, I mean, it is incredibly easy to underestimate the concrete floor.
Yeah, you'd think concrete is just concrete.
Right, and leveling a CNC lathe is widely misunderstood as just making sure the machine sits flat.
Yeah.
Like, you know, shoving a coaster under a wobbly table at a restaurant so your water doesn't spill.
But a CNC machine isn't a table. It's a massive, multi-ton block of cast iron.
And that massive weight is the core issue. Leveling is actually about controlling the internal stress state of the machine bed.
Internal stress state.
Yeah, if a 10-ton machine is resting on a floor that isn't perfectly supportive across all its leveling pads, gravity pulls down unevenly on different sections of the iron.
Okay, I'll follow.
That uneven pull actually twists the heavy machine bed.
Wait, hold on. You're saying a solid block of cast iron actually twists? Micro-twists, yes.
Oh, wow.
And when the bed twists even a fraction of a degree, the pristine alignment of the guideways is completely corrupted. The geometric relationship between the turret holding the tool and the spindle holding the metal is shifted.
So the entire mechanical chain loses rigidity.
Exactly. And furthermore, altering that internal stress state actually changes the machine's natural frequency. So it opens it up to entirely new resonance hazards.
I really want to make sure the listener is grasping how wild this is. Are you telling me a machine can be installed in January, pass every single cutting test with flawless precision,
Right.
but by July, just because the concrete floor settled a single millimeter under the weight, it hits a new resonance zone and starts vibrating uncontrollably?
A single millimeter of settling is more than enough to trigger a complete catastrophe in high-precision machining.
That is insane. Hollow spots in the concrete that cave in over time, anchor bolts that slowly stretch, or just the natural geological settling of a foundation. It completely changes the machine's center of gravity and its support stiffness.
And the tragic part is, the symptoms look exactly like a tooling problem.
Yes, they do.
An operator will see chatter marks or unstable dimensions, and they'll spend like 3 days, frantically swapping out carbide cutting inserts, changing feed rates, recalibrating software.
Completely blind to the fact that the literal dirt under the concrete is the actual culprit.
This is why the absolute golden rule in our sources is to record baseline leveling data the day the machine is installed.
You must have a reference point. If a machine suffers a crash, if you move it across the shop, or if you suddenly start seeing an unexplainable drift in accuracy, your very first diagnostic step is checking the foundation.
Because a weak foundation stops absorbing acoustic energy and acts like an amplifier instead.
Yeah.
Okay, let's assume the floor is perfect.
Mhm.
The concrete is cured, the anchors are tight, the bed is totally stress-free. If the vibration persists, we have to look inside the machine.
Right, into the internal components.
And the texts detail this terrifying concept of coupling effects, where the internal components essentially declare war on each other.
Yeah, it's a slow internal rot. Let's start with the spindle bearings. They are the heart of the rotational accuracy.
Right.
They hold the massive spinning chuck steady against the immense forces of cutting steel. And their failure is rarely sudden. It tracks across 3 distinct observable stages.
In the early stage, the sources talk about a loss of preload and an increase in radial runout. For the listener who isn't a mechanical engineer, what is physically happening inside that bearing?
Preload is the engineered tension applied to the bearing to keep the rolling elements tightly packed without any slop. It's what makes the bearing feel stiff.
Okay, and radial runout.
That's essentially wobble. It's how far the spinning shaft deviates from a perfectly true center. In the early stage of failure, microscopic damage occurs on the bearing raceways.
So the preload drops slightly.
Yes, meaning that tight packing gets just a tiny bit loose. The runout increases, so the metal being machined is wobbling a microscopic amount.
And the trap here is that the machine is probably still passing quality control at this point.
Usually, yes.
The parts look okay, but the operator might notice the machine sounds a little different, maybe a higher pitched whine.
Precisely. The high-frequency noise is your only real warning. If you ignore it, you enter the middle stage. The internal clearance inside the bearing widens significantly.
And that's when things get bad.
Right. Now, the physics of cutting really turn against you. As the heavy chuck spins at high speeds, centrifugal forces want to pull it outward. Because the bearing has lost its tight preload, it no longer has the stiffness to resist that outward pull.
So the spindle axis is physically pushed away from its center line during the cut.
Exactly. You start seeing severe surface roughness, and those impact loads start chipping the edges of your cutting tools.
So if the middle stage is where the wobble is bad enough to start shattering tools, the late stage must be total mechanical collapse.
The rigidity completely vanishes. The spindle actually deforms under the heavy force of the cut.
Ouch.
And because the structure is now weak, the natural frequency of the entire spindle system drops dramatically. It brings it dangerously close to the operational cutting frequency.
And when those two frequencies overlap,
You get catastrophic self-excited chatter. The noise is deafening, precision is impossible, and no amount of software tweaking will save you. You are replacing the bearings.
wow. And there is a parallel death spiral for the ball screws, right? The long threaded rods that control the feed motion.
Everyone's moving the heavy turrets back and forth with pinpoint accuracy.
Yeah.
The ball screws degrade on a very similar timeline.
How does that start?
In the early stage, you lose the preload on the nut or the support bearings get slightly loose. You experience something called dead travel.
Dead travel.
Yeah. When the machine tells the tool to reverse direction, the motor turns. But because of the internal slop, the tool doesn't immediately move. It hesitates, or it crawls unevenly at low speeds.
It's sloppy. And I imagine that slop means the servo motors are suddenly slamming components around instead of pushing them smoothly.
That brings you right to the middle stage. The immense torque from the servo motors turns into physical, hammering impacts against the loose mechanism.
Like taking a hammer to it.
Basically, under heavy cutting, the circulation of the steel balls inside the screw becomes chaotic. That violent internal vibration travels straight through the machine's guideways and right into the turret, physically distorting the path of the cutting tool.
The sources mention the late stage involving axial movement and fretting wear. Can you break those down for us?
Sure. Axial movement means the looseness is so severe that the entire length of the ball screw is shifting back and forth along its own axis when the cutting load hits it.
Oh, man.
It acts almost like a slide whistle, creating a deep, low-frequency structural resonance that just shakes the entire lathe.
And fretting wear.
That's the microscopic consequence. When two tightly fitted metal surfaces vibrate against each other continuously, they undergo microwelding and tearing. They literally grind each other into fine metallic dust.
which perfectly illustrates the coupling effect. These systems do not live in isolation.
Not at all.
I mean, think of it like human anatomy. If you injure your knee, you instinctively start walking with a strange limp to avoid the pain.
Right.
But that weird, uneven stride puts abnormal, twisting stress on your hip joint. A year later, your knee still hurts, but now your hip is completely destroyed as well.
That is the exact dynamic inside the lathe. Feed instability from a loose hammering ball screw creates fluctuating cutting loads, which violently stress the spindle bearings.
And it goes the other way too, right?
Yes. If the spindle bearings are failing and vibrating, that high-frequency shaking travels down into the heavy cast iron bed and causes fretting wear on the ball screw supports. They systematically destroy each other.
And the research highlights a terrifying detail here. This degradation is not linear.
No, it's really not.
You don't get a slow, steady increase in chatter over 3 years. You hit a critical clearance point like a specific threshold of wear, and the machine instantly jumps from seemingly stable cutting into violent, uncontrollable chatter.
You essentially fall off a cliff. This is why modern predictive maintenance relies so heavily on vibration monitoring sensors.
Because they can see the drop coming.
Exactly. If you analyze the frequency signatures early, you can spot the damage. Spindle faults create high-frequency noise tied to the rotational speed. Ball screw looseness creates low-frequency harmonics tied to the feed rates.
You can detect a limp before the hip shatters, to use the analogy.
Precisely.
Okay, so we have mapped out the entire dynamic ecosystem, from the settling dirt under the concrete all the way up to the microscopic fretting wear in the ball screws.
We know the enemy.
Right. Now, how do we systematically destroy it? As you mentioned earlier, the instinctual reaction on the floor is to just aggressively slow the machine down.
Which we know is a terrible strategy. The very first step in the systemic fix is reducing the excitation forces. You balance your rotating parts.
Like the chucks?
Yes. Check the chucks, the jaws, the pulleys. If you are using a hydraulic chuck, you have to verify the clamping force is perfectly symmetrical.
Because even a tiny error gets magnified.
Huge. A tiny alignment error might seem insignificant, but when it's rotating at 3,000 revolutions per minute, it transforms into a massive repetitive hammer blow against the bearings.
Let's say you balance everything. The machine is level, but chatter still erupts during a cut. What is the golden rule of troubleshooting the parameters?
Change one single variable at a time. Never change your depth of cut, your feed rate, and your speed simultaneously.
Because then you wouldn't know what actually fixed it.
Exactly. You will never know. And crucially, you always adjust your spindle speed first.
Why spindle speed first? Why not just take a shallower cut so the tool isn't working as hard?
Because chatter is fundamentally a problem of overlapping frequencies. It is that resonance issue we discussed earlier with the wine glass.
Right.
Sometimes tweaking the spindle speed by just 5 or 10%, and surprisingly, often increasing the speed changes the frequency of the tool impacts just enough that they no longer overlap with the machine's natural frequency.
So you break the resonance loop.
You break the loop, the singing wine glass stops vibrating, the chatter vanishes instantly. Once you find that stable acoustic zone, then you can optimize your feed rate and cutting depth.
Here is where the text gets incredibly interesting, delving into the physical geometry of the cutting tools.
Yeah, the tooling counterintuitions.
There's this fascinating nugget regarding the nose radius of the tool-like, the rounded tip, that physically peels the metal away.
Yeah.
Normally, a large sweeping nose radius is highly desirable, right? Because it wipes the metal smooth, leaving a mirror-like finish.
Typically, yes.
But the sources state that in a weak setup, a large nose radius is actually a massive liability that triggers chatter.
It all comes down to the physics of radial force. When a cutting tool engages the metal, forces push in multiple directions. Radial force is the pressure pushing directly backward.
Away from the spinning part.
Yes, straight into the tool and the machine structure. A large, sweeping nose radius spreads the cut over a wider area, which dramatically increases that backward radial push.
You are basically pushing a blunt object against a system that doesn't have the backbone to resist it.
Exactly the problem. If your machine is incredibly rigid, it easily absorbs that high radial force and you get your perfect shiny finish.
But if it's worn out,
If it's worn out, or you are cutting a long, slender, flexible piece of metal, that immense backward push acts like a loaded spring. It physically bends the metal back, the metal snaps forward, The tool bounces, and you immediately trigger that self-excited washboard loop.
Oh, wow. So what do you do?
In a weak setup, you must switch to a sharper tool insert with a much smaller nose radius to slice through the metal with minimal backward push.
That makes total sense. The sources also harp on the boring bar length to diameter ratio. For anyone who doesn't know, a boring bar is the long cylindrical tool used to reach deep inside a hole to cut the interior walls.
Think of a boring bar like a diving board. The longer a diving board is, and the thinner it is, the more wildly it bounces when you step on the end of it.
It's the exact same physics for internal machining.
Absolutely. If your boring bar sticks out too far past its support base relative to its thickness, it loses all structural rigidity. It just becomes a metal diving board bouncing under the cutting pressure. Managing that overhang ratio is absolutely non-negotiable for stability.
We've checked the floor, the bearings, the resonance, and the tools. But the texts outline a final perimeter of defense outside the cutting zone altogether: the environment and damping.
You cannot isolate a machine from its environment. You really shouldn't place a high-precision CNC lathe next to a massive stamping press that's sending shock waves through the floor.
That feels like common sense, but I'm sure it happens all the time.
Constantly. You also have to tightly control the ambient temperature of the shop. Extreme heat causes the massive cast iron bed to undergo thermal expansion.
That what swells up.
The metal grows and distorts, which completely ruins the delicate leveling you performed on day one, throwing the entire system out of alignment.
And if you've exhausted all mechanical and environmental fixes, the final step is damping, both passive and active.
Passive damping is relatively straightforward. You integrate materials like heavy rubber, specialized polyurethane pads, or tuned mass blocks into the machine's foundation or structure.
They act exactly like shock absorbers on a car, right?
Yes. They physically soak up the acoustic vibration energy and dissipate it as microscopic heat. Active damping, however, is the cutting edge of manufacturing defense.
How does a machine actively fight its own vibration?
It uses sophisticated sensor arrays. Accelerometers constantly monitor the vibration signatures in real time. The moment they detect the specific frequency of chatter beginning to form, the computer triggers control elements.
Like what kind of elements?
Like piezoelectric actuators or electromagnetic forces, they instantly emit a counterforce. It physically pushes back against the structure at the exact opposite frequency to cancel out the resonance wave before it can escalate.
That is incredible.
It is, but the texts issue a stark warning here. Damping, no matter how advanced, is the absolute last step. You cannot actively damp your way out of a destroyed spindle bearing or a hollow concrete floor. Mechanical health comes first.
So what does this all mean for us? Looking at this towering stack of technical engineering texts, the grand takeaway isn't just about cutting steel.
No, it's bigger than that.
It is a profound lesson in systems thinking. Fixing a complex problem is never about slapping a digital Band-Aid on a noisy symptom.
Exactly.
Whether you are troubleshooting a slant-bed lathe, managing a dysfunctional corporate department, or debugging a massive software architecture, the logic holds true.
The principles are universal.
Treating the root cause, verifying the foundation is solid, hunting down the slow, invisible wear, and deeply understanding how interconnected components stress each other is always superior to just dialing down production to survive the day.
It really requires a fundamental shift in perspective. You have to stop staring obsessively at the tool and start interrogating the environment that permits the tool to function.
Exactly.
And considering the trajectory of that active damping technology, well, it forces you to wonder about the future. As manufacturing pushes toward ultra-precise, AI-driven automation with cutting speeds that are unimaginable today, the margins for error will effectively disappear.
So where does it go from here?
Will the autonomous machines of the future require the physical ability to actually feel their own concrete foundations settling beneath them? Will they need the intelligence to dynamically shift their own internal center of gravity in real time just to survive the sheer violent forces they themselves are creating?
Man, it brings us right back to diagnosing the hidden disease. The X-ray machine of tomorrow might not just show you the broken bone. It might highlight the exact structural flaw in the concrete sidewalk that caused you to trip in the first place.
That's a great way to put it.
It is a murky, incredibly complex world out there. But if you step back and look at the whole system, the invisible finally becomes visible. Keep hunting down the root causes in your own life, and we will see you on the next deep dive.